Hello students, good morning to all. So welcome back again in the subject of Dynamics of Machine 2, where we discuss the chapter number 3, Damped Free Vibration. Okay, so before going to start the session, let us discuss what we have discussed in the last session. In last session, we have discussed the two case number 2, where the zeta is equal to 1, that is what critical damp system, and we got the response of that critical damp system, right? So this is what the critical damp system, and here is the response of critical damp system, right? So what we learn from this here is, this is the equation, or we can say a solution of your second order differential equation, which is nothing but your response, right? The response means it is the graphical representation of that amplitude versus its time. Okay, so this is what we call it's a response, that how the system will vibrate with respect to the time. At a particular time, the displacement is here, at next time here, and so on, right? So this is what we call the zeta is equal to 1, that is critical damp system. And we discuss one more case, that is the under damp system, if the zeta is less than 1. And here is the response equation and the response. So this is the equation of the displacement with respect to the time t, right? And this is what the response. Here we come up with two parameter from this, which is called omega d. This is nothing but your damped natural frequency, and we come up with this new TP, that is called time period, right? TP is equal to 2 pi by omega d. So these two parameters that we can get from this response. So as you can compare the three cases, first zeta more than 1 is over damped system, zeta equal to 1 is a critical damped system, and zeta less than 1 is called under damped system. The first two case, they were considered to be as a non-vibratory system. It's a aperiodic motion, right? So we cannot consider that motion in a vibratory system, because it's itself not considered to be as a vibratory motion, right? So here the only underdamped system is to be introduced in a particular mechanical vibration system as a damper, which is used to retard the motion, right? So this is the only case we generally prefer in mechanical system to resist the motion, to retard the motion, right? Now next, that what we are going to learn today is new term which called logarithmic decrement. Okay, so the next topic that we are going to learn here today is a logarithmic decrement. It is called delta. Okay. This is a new term, or we can say new topic of this chapter of damped vibration, logarithmic decrement. What is logarithmic decrement? Right? What does it mean itself? Beside the decrement. Okay, so it is somewhat related to what that amount of amplitude has been reduced, has been decreased. Okay, at what rate? That is nothing but your logarithmic decrement. So let us understand that concept here again by drawing that response curve. If I consider, this is what, okay, so this is the zero mean line. Over this axis we have a time t in this direction, so it is 0 and it is going to be increased as in this direction of x, while in y direction we have another parameter called displacement x, right? And if you draw the diagram for a particular critical dam system, it is somewhat like this. it has been reduced gradually, right? Every cycle, certain portion of energy has been decayed and system will be now in equilibrium like this. So every cycle, there is a certain amount of reduction that has been taking place here, right? So if I consider here as this point from here to here, if I consider this point from this end to this is nothing but that amplitude we call as the x1. Okay, this is what the amplitude x1. If I consider this is the amplitude, if I say this is x2, same way here, this is the amplitude for a third cycle, x3. This is what the amplitude we call x4, and so on. We have a number of amplitude, and every cycle there is a reduction, or we can say decrement in the amplitude value, right? And what is this called from here to here is your time period. Okay, this is what time period, right? So this is what the behavior of a regular damped vibratory system, right? Now, what is this decrement? Or we can say every cycle, there is some amount of decrement has been taking place or observed. That rate, at what rate, there is a decrement in its amplitude value for a particular case. That is called its logarithmic decrement. Okay, so what the logarithmic decrement? The rate of decay, sorry, the rate of decay of an amplitude is measured by the parameter which is known as logarithmic decrement. At what rate the amplitude has been reduced, that is called as the logarithmic decrement, right? Or you can even define in other way also. The logarithmic decrement is defined as, how we can define? Okay, so what shall I define the logarithmic decrement? How we can define? It is defined as the natural logarithm of the ratio of any two successive amplitude on the same side of the mean line. Right? This is what we call logarithmic decrement. It is the ratio of any two successive amplitude. Successive amplitude means what? Let us consider this is x1, this is x2. Okay, so this x1 and x2 are called successive amplitude. Same way x2 and x3, these two are called successive amplitude. Same way x3 and x4. If you take the ratio of any two successive amplitude, so let's take the ratio of x1 by x2, or you can take a ratio of x3 by x4, you can take ratio of x2 by x3, right? That ratio, but what it is, it's natural logarithm, not only the direct ratio. The natural logarithms of this two amplitude ratio is called its logarithmic decrement. So let us derive the equation of this logarithmic decrement for any damped vibration case. Okay, so let's go for its a simplified derivation here. What we can say here, so let us consider here in this case, what we can consider here at this time. Let us consider this is the point, you can say point P. Let us consider this is another point P, Q. This is what say R and so on, right? So here, if I say the system is at point P at a particular time T, right? So what should be the amplitude here is X1, right? And similarly for point Q, you have a time period, let's say T2, and displacement is X2. So what is this time period? Okay, so this is what we call, this is nothing but your time T1, I said, right? This distance is what time T1, and if I said this distance from here to here, this is the time T2, right? We have start from here, 0 time. After a few seconds or maybe 0.01 second, 0.02, few minutes, not just like as 2 or 3 or 5 second. Just all the values is in a fraction of the second value. So if a fraction of the second, the values of the amplitude is somewhere here, let's say x1, and time is t1. Similarly, at point q, the time is t2. After the time t2, the amplitude is at reach at q point, that is x2, right? So if I say the time period is the distance, or we can say time required to complete a one cycle from here to here. So as per geometrically, we can say that time period is the difference of these two, right? So what we can write here, the time period Tp is equal to T2 minus T1, right? Can I write in this way? T2 minus T1, because from here to here is a T1, from here to here is a T2. So what about this distance now? It is obviously difference of these two. Fine. Here. Any doubt? Any of the student? Is it clear how we'll get this time period in terms of time T1 and T2? You can ask if you have any doubt on this. As I said, is it clear to all? Yes or no? Kindly respond quickly. Okay. Okay, fine. Hardik, I'm repeating again what it said. What we want to find out is, I want to find out the time required to start it at from P and reach back to the point Q. The time for this cycle is nothing but your time period TP. Now, if I at point P, we have started from here, after a few, or we can say fraction of second, let's say T1 second, after T1 of time, your position of your displacement is at point P, let us say. So if you want to reach from here to here, it's take a time T1, let's say. Same way, again, it point is goes in this direction, and at here, at a point Q, from the zero line, it's take a time T2. Okay, because this is, let us say, x1, t1, x1 is the amplitude, t1 is the time, and here I suffix it for 2. That's why I mention here time t2. Okay, so what we call the time required to reach at that point Q is t2, and at that point Q, the displacement of the system is x2. What is said? Okay, x2 is what? The displacement, or we can say amplitude, after the time t2, or we can say at a point Q, right? So I want to measure this gap, or we can say this distance, that is nothing but time period Tp. So what is this Tp? It is the difference between this distance T2 and the small distance T1, right? So T2 minus T1 is your time period here, right? And as you know, what is the time period as per our previous case? What is the time period here? Time period equation is known. Okay, you can see here 2 pi by omega d. That is what we call time period. So we can directly write here that this is nothing but 2 pi by omega d. Right. So this is what your time period here. Okay. Now, what next after this? So as also you know the time period equation. So this is what further you can write. This time period is equal to 2 pi as it is. And what about omega d? That you know already. It is nothing but 1 upon, under root of 1 minus zeta square into omega n. This is the equation of your time period. Okay. So we are using the same existing equation. We are not doing anything new here. Now we have to do what is the time here, right? So to get the time t1 and t2, we just want to find out the time t1 and t2, and we just write the values in that aspect. Okay, so just recall the amplitude equation, or we can say generalize the displacement function. The equation of, we can say, the response of the system of your under dam system. Okay, so what is the equation? Just try to recall that equation here. X is equal to capital X e to the power of minus zeta omega n t into sine of omega d t plus 5. Okay. Again, I said this is not a new thing. We are using the same equation as we already obtained here. You can see x is equal to capital X e raised to minus zeta omega and t sine of omega d t plus 5. Right. This is my first equation. Now, if I want to find out the response, okay, what I need to do is I need to use t1. So here I'm writing again. If I'm writing x1, it means at this position of point P, the displacement is x1 and time is t1. So I'm just replacing that term here. This x is it is e raised to minus zeta omega n. Now it's a t1 sine of omega d t1 plus 5. Okay, so this is what we call x1. Same way, you may also get the equation of x2. What is the x2 here? Same way, get the equation for x2, capital X e to the power of minus zeta omega n t1 into, sorry, t2 into sine omega d t2 plus 5, because now we are finding the displacement after the time t2, that is your x2. Fine. So these are the x1 and x2. Now what we have to do is we have to write this equation in terms of t and in terms of the x. Okay. So first do write this thing and then we'll proceed for the next derivation. Okay. So complete this first and then we'll go for the find out the derivation of time period and logarithmic decrement. So kindly complete this item first, then we'll move for the next step. And let me know once you finish in a chat box. Okay. Just simply typing a done. Yes, Mohammed, is there any query from your side? Which part that you not clear? Mohammed? Okay, for writing. Okay, fine. Good. So let's move for the further part of this simplification, or let's say derivation. Now what we have to do is here, we just replace this T2 from this relation. Okay, so this is what TP is equal to T2. So here what we can write from this, here from this we can write that T2 is equal to TP plus T1, right? Because this T1, if it goes toward the side, it is nothing but summation with this TP. So T2 is equal to TP plus T1. We are using this relation in this equation, and let's write it further, is equal to x e to the power of minus zeta omega n. Now this T2 has been replaced with T1 plus TP. Okay, so TP plus T1 into sine of omega d into again T2, so that we can write TP plus T1 plus phi. Right? Now further write this equation x e to the power of minus zeta omega n Tp plus T1, that term as it is, into